So we want to maximize x plus y over the unit circle. Okay? And I want to emphasize what this looks like geometrically first, and then we'll get into how to set up Lagrange multipliers. So geometrically, we've got this unit circle. Right? And now we'll draw a contour plot of x plus y. Okay, so we'll plot x plus y is 0, right? That will be a line through the origin like this. Okay, when we do x plus y is equal to 1, pass through those intersection points with the axes. Okay, we get the sense that as we increase this right-hand side, the curve is moving away from the circle, moving away from the origin. Okay, so the largest value of x plus y on the circle is when this line is tangent to the circle. Okay, so our goal now when the resulting line will be tangent to the circle. After that point, right, for guys like this, we no longer touch the constraint. Right? So we no longer touch x squared plus y squared is 1. So we want the very last line that touches that circle. Okay, so what we'll do is we'll set up a way of finding that point of tangency. Okay? So Lagrange, his observation was that if we look at the gradient of x plus y, it's always pointing in the same direction. You've got this family of gradients that are all pointing away from the circle. And then on the circle, we've got another family of gradients. And when those two gradients are pointing in the same direction, we found the point of tangency. Right? So we've got this blue family of gradients and this green family, and when they line up, we found the point of tangency. Okay? So let's look at that algebraically. So what does, okay, so let's name our constraint and name our function. So we want to maximize this guy subject to this given constraint. To do so, we need the gradients are parallel. Okay, so one way for them to be parallel is for the two gradients to just be equal. Right? If the two gradients are equal, then they're parallel. But we can also stretch the gradient a little bit and remain parallel. Okay, so this is the condition that those two gradient vector fields line up. Okay, so let's do the algebra of that. So we take our function f, calculate its gradient, we get 1, 1. Gradient for g, okay. These constraints. Yes, there's a question?
Can you just show again what you meant by tangency occurs when the gradients are parallel?
Yeah. Right, I think I'm gonna like redraw the same picture, but really big this time. So this is just like such a nice and just beautiful thing in geometry. So what do? You take your circle, and it has a gradient vector on it. This guy, 2x, 2y. So that's showing on the circle the direction of maximum increase of g. If you want to make g as big as possible, you go in that direction. Okay. Now we've also got this constraint that we're working, or sorry, this goal function x plus y. Okay. And it's got a gradient on it. So what we want to do is we want to move the green line until it's tangent to the blue circle. At that point of tangency, we're going to have two gradient vectors. Right? As this green line comes up, it'll overlay on top of this blue line. And at the point of tangency, we'll get some picture like this. Okay? Those two gradient vectors will sit on top of each other.
What does it mean for the gradient to increase, or like the direction of maximum increase to be away from the origin and the circle in R2 is just going off it?
Right, yeah. So that's saying that if you're looking at this function g, right? The function g will give you a parabola. Right? And it's saying that the the way to increase on that parabola fastest is to go away from the origin. So the direction of maximal increase on a parabola is always away from the origin.
But for that circle, so like what is the gradient mean in relation to that circle?
Right, okay, so. Okay, so that circle in the plane, our constraint, is this circle here, right? And that circle is part of a bigger family of circles, right? And the gradient on that family is pointing away from the origin. Or I should draw it so it looks more convincingly like this. It's pointing up the parabola and away from the origin. Does that help?
Yeah.
Does that clear thing up?
So if you were looking at the point where like the parabola and the circle touch, would it be in the same like direction as the parabola? Or would it be perpendicular to it?
So the parabola and which touch?
So like over here where we have the circle and the parabola, at the two sides, the parabola and the circle touch, right?
Yes, yes.
So would the gradient follow the parabola at that point? Or would it be
Right.
perpendicular to it?
So the gradient vector field is drawn here, right? So the gradient vector field is pointing outwards from the origin, and it's a vector field in the 2D plane. So it's pointing, like, here I can draw on a couple of arrows. It's pointing like in the plane, not up the parabola. Does that answer the question?
Yeah.
Cool. And it's in 2D because it's pointing at a direction of travel. Right? Saying which direction do you have to move to go up the parabola as fast as possible. Okay, nice. Yeah, these are sweet questions. Okay. So we've got to here, we figured out what we need to solve to get parallelness. Okay. Great. So we can, oh yes, so we can rearrange and solve for this letter lambda. Just say what that is. So this is a Greek letter lambda. It's just another constant. It just means that we're stretching the gradient of this guy until we get the gradient of this guy. I think that it's lambda because Lagrange came up with this idea. Okay, so what do? We can rearrange these guys to solve for lambda. This. And now, that tells us that x and y have to be of equal values. Okay, so now we can substitute that in here and get a value for x and y. So we substitute in here, we solve for x, we get plus or minus 1 over root 2. Okay, so the point of tangency we actually get 2 points of tangency now. Right, we get this one where x and y are positive. And where x and y are both negative. Okay, so this guy will correspond to the maximum of x plus y on the circle, and this guy will correspond to the minimum of x plus y on the circle. Okay. Yeah, question?
They're both the same Z value.
No, they're different z values. So this will be 2 over root 2. This will be negative 2 over root 2. Yes?
But we would technically only want the positive one because of the question.
Yeah, because we're looking for a maximum. Right? So this guy will give us the max.